So logs. Logs are really, really important. They are going to allow us to solve an equation that we've never been able to solve before. And the one at the top there, 4 to the power of x is equal to 50, is something that we've never been able to work out the value of x for. But using logs, we are going to be able to. And I've said in my notes, just as squaring and square rooting are inverses, all we need is the inverse function for this exponential function to be able to unlock the value of x. And they're called logarithms. I've got two equations here. I've got y equals something to the power of x, where that value, that b value will be some constant, just like my 4 to the power of x in that slide. And the inverse of that top equation, the inverse of y equals b to the power of x, is that x will equal, so that power that we don't know, will equal the log, and you say log to the base b of y. Okay, so that is this probably single most important thing that we need to be able to do. We need to be able to remember this, and we need to be able to switch between the two of them. So y equals b to the power of x means also that x is equal to log to the base b of y. And we're going to practice switching between those two today. And I'm also going to teach you some other stuff as well to let you hopefully be able to get you through 2 exercises. You can go forwards and backwards on these. So if you see something written like this and want to turn it into the top version, then that's absolutely fine. We can check, hopefully you've got your calculators with you. We can check that this works really easily. Okay, I've got an example of the fact that 3 squared is equal to 9. So if we look at the setup of that, I've got my y is my 9, my b is my 3, and my x is the 2. So that should mean that if we get our calculators out, that should mean that 2 should be the answer when we type in log to the base 3 of 9. And I've got my calculator with me. We've got a log button. It says log, and then there's like a coloured in blob and then an empty blob. If you press that button, and then it'll let you type in the 3 for the base. That little number is called the base. And then if we move across and put the 9 in the brackets, when we press equals, you should get 2, and I do on mine. Okay, so that shows that if we didn't know what log to the base 3 of 9 was, then we'd be able to get our calculator to work it out. It also means that if we didn't know what power we use to get from 3 to 9, that we can work it out. We can work out that x will be log to the base 3 of 9. Okay, so that's extremely useful. I'm going to go back to the example from earlier. It's not as easy for this one because the answer is not going to be a whole number, but that's even more useful. That means if we put this in log form, then we're going to be able to work out the value of x. Okay, and for this one, b is my 4, the base is 4, so that means I'm going to need to do log to the base 4 of 50, and that will give me the answer of x, log to the base 4 of 50. And if we type that in on our calculators, log to the base 4 of 50, then I'm getting an answer of 2.8219. You could go backwards, you could check that. If you put in 4 to that power now, you should roughly get 50. So 4 to the power of 2.8219, I'm getting 49.998. So it works. You can go forwards and you can go backwards. So that's going to be really, really useful. So just going to go through some examples of kind of what you're going to be needing to be able to do to get through exercise 14D. And then I'm going to keep going. I'm going to go and teach you some extra rules that are going to be useful for a lot of year 13 maths that will help you with exercise 14E. What I'll say is the questions that we're about to look at now, this first set of examples they're not exam questions. They're not, you wouldn't be asked to do this in an exam. But what these examples are useful for, and what the exercise is useful for, is if you get stuck on logs kind of halfway through year 13, then I would recommend that you come back to these examples, you come back to this exercise 14D, and it will refresh your memory and it'll help you loads with your other work, even though these particular examples aren't common to what you'd be given in an exam to answer. So it says, by rewriting without the logs, work out the following. So we just need to go from, so if this is my x, we're trying to work out the value of x. We need to write it in this form because it says get rid of the logs. So we need to go backwards. So we need to think about where the numbers need to go, need to fit into the equation. So we've got the base is the 3, so that's my b value in the top equation. So I've got 3 to the power of x is going to be equal to 81. The 81's my y value. So all it wants us to do is think about what the answer to that is. What power of 3 gets us to 81? Well, it's not squared because that's 9. It's not cubed because that's 27. It's 4. 3 to the power of 4 is 81. So that's the answer. That's us working out the answer. We've got another example. We can do the exact same thing. If I put an x here, my base is the 4 this time. So it's 4 to the power of x needs to equal 0.25. You might not know the answer to that one straight away, but if I rewrite that as a quarter, that might help you. How can 4 to the power of something equal a quarter? Well, that's when it's -1. Okay, so if you were to type this on your calculator, log to the base 4 of 0.25 would give an answer of -1. I've got a slightly different one here, and this is to illustrate one of the things that we're going to learn later on. Log to the base b of b to the power of 5, what's that going to equal? Well, our b is the base, so b to the power of 5, and all of this is the y. So we've got b to the power of 5 here. So log to the base b of b to the power of 5 is equal to what? Well, it must be equal to 5 to make these powers match. So that means that log to the base b of b to the power of 5 is equal to 5. And that's not a coincidence. That's not a coincidence that the power here is equal to that answer there. We're going to come back to this rule later on today, and you'll see it reappear in another form. So my next few examples are kind of going the other way, and I've taken away my little cheat sheet because you're not going to have this available to you all the time. You're going to need to be able to work with this yourselves. So if we have a look at this one, 4 to the power of 5 is equal to 1024. Now that's just a fact. That is true, that 4 to the power of 5 is equal to 1024. We want to rewrite that using logs, okay? So at this point in time, I'm not expecting you to be able to just write that down straight away. What I would expect us to need to do is rewrite those little rules that we've just had that have been helping us. That if y is equal to b to the power of x, then x is equal to log to the base b of y. Now, I remember very vividly learning about logs, and I could never remember when I first started learning. I could never remember this relationship, and I had to go home and I had to write it down like 10 times, and then I never forgot it. You've got to know this relationship, okay? Really, really, really important. Once we know this, it will unlock loads of different questions that we can answer. So now that we've written it in the form that we want, we just need to pick out which bit's which. My base is the 4, so I can write that log to the base 4. My y is the 1024. And the x is the power in the top equation, so that's going to be the answer. So log to the base 4 of 1024 will equal 5. And you can check that on your calculator. If I grab my calculator, I was expecting. I've got another example here. 3 to the minus 2 is equal to a 9th. That's another fact. We know that that's true. If again, I write my relationship down between the exponential and the inverse, the log, then I can just apply that to my question. This time 3 is my base. So log to the base 3 of a 9th has to equal the power, has to equal minus 2. And again, we can check that on the calculator. Log to the base 3 of 1 over 9. And it gives me my minus 2, which I'm expecting. Another thing we can do is similar to these ones, but we're now having to fill in an unknown using that relationship that we've been talking about. So I'll write it down again. Y is equal to b to the power of x. Hopefully you know what I'm going to write down here. X is equal to log to the base b of y. We're in this form now. We're in that bottom form. Don't worry that I've used an x here. That's quite common. That's just to try and put you off. That's trying to try and confuse you. We just need to keep everything matched together. So my 5 is my base, so that's going to be my big number. My y is my x, so that is going to be this number. No, it's not. That's going to be my power. See, I'm getting muddled up now because of the different use of the letters. So my 4 is this x here, and that needs to become my power. So 5 to the power of 4 is equal to this x, which is the y. So that's equal to y. So 4 to the power of 5, I don't know that offhand. Do I? Is it 625? Yeah, it's 625. So I should probably have written x there. So x is equal to 625, and we can check that. We can check that by typing it back in. Is log to the base 5 of 625? Does the calculator tell me the answer is 4? It should do. Log to the base 5 of 625. Yeah, the calculator is telling me 4. So we know we're right. Let's try another one like that. It's a bit more complicated this time. We've got our original relationship. I'm writing it backwards because these have been written backwards. Log to the base b of y is equal to x. Because that's then going to allow me to write that this is my b, this is my y, and this is my x. And then I could just stick it in here. So we've got 3 3 to the power of the x term is 4 needs to equal 4x plus 1, the y term. So we've got to work out x. There's a little bit more work to do this time. 3 to the power of 4 we know. 3 to the power of 4 is 81. I'm going to subtract 1 to get 4x, and I'm going to divide by 4 to get 20. So that's the answer to this one. Log to the base 3 of 4x plus 1 equals 4 means that x needs to be 20. Okay? I've got one last one down there. 5 to the power of x is equal to 60. Again, if we've got b to the power of x is equal to y, then log to the base b of y is equal to x. Here's my b, here's my x, here's my y. So we've got to go backwards this time. We've got to turn it into the log. So we'll work this answer out. It's going to be log to the base 5 of 60 will be the answer for x. And again, we're just going to grab the calculator and let it do the work for us. Log to the base 5 of 60 gives me an answer of 2.54 when I round it. So the next part, and this is again just as important as that first relationship that I've just introduced you to. There are 3 main laws to do with logarithms. Now, you don't have to learn the proofs of these. The textbook might go through the proofs of these, and if you're interested, have a look. If you want to go on YouTube and find out the proof of these, that's absolutely fine. They are quite interesting. Well, I think so. You might disagree, but you don't. There's no requirement to know these proofs. You do have to know the rules, though. The rules aren't given in your formula booklets, so you do have to know these forwards and backwards. And with same as the other rule that we've just learned, these can be used forwards and backwards. So you can go from left to right, and you can go backwards from right to left. So they look a bit weird. They look a bit scary. The first one, if we just look at the first one, that's the multiplication law. And what that says is if you are adding 2 different logs, as long as they've got the same bases, that base number has to be the same. If you're adding 2 different logs together, then you can turn it into a single log, but you times the values together rather than add them, okay? So a quick example of this would be that if I had log to the base 4 of 3 plus log to the base 4 of 2, that would be able to be written as log to the base 4 of 6, because I can times the 3 and the 2 together and create one log. And in a lot of the work you're going to want to do, you're going to be wanting to reduce the number of times you've got log written down, basically. So if you can rewrite something as a single log, then that's going to be really useful. Again, you could, if you wanted to, you could split this. You're unlikely to want to split a 6, but you might want to split like a 3x. So if I had log to the base 4 of 3x, it might be useful to write that as log to the base 4 of 3 plus log to the base 4 of x. It might not, but it might be. And you can, if you want to. You can go forwards and you can go backwards. The next law is the division law. Very similar to this one. But if you are subtracting one log from another, then that's the same. As long as the bases are the same, then that's the same as the single log of the x over the y. So the first one over the second one. And finally, the power law says that if you have a log with a value that has a power in it, then you can take this power and just move it to the front and times by that log instead. Okay, so log to the base b of x to the power of k is the same as k times the log without that power. And that's really useful. We use all three of these all the time, but you'll probably find that you're using that bottom one the most. Okay. So there's a few special cases, and some of these come from the work that we've already just looked at, and some of them come from these three new laws that we've just learned. The top one I would actually say comes from that original relationship that we've just looked at. And that is that if you have a base matching the term that you are logging, then what that's equivalent to, if you look here, that's equivalent to you saying that b to the power of what is equal to b. And it's 1. B to the power of 1 is equal to b. So when the base matches the value that you are logging, the answer is always 1. So log to the base 4 of 4 is 1. Log to the base 7 of 7 is 1. Log to the base t of t is 1. And that's something that you're going to want to try and remember. None of this is in your formula booklet. Okay, the next one combines this rule and the power rule. Okay, notice I've got a power here, and we've just learned that we can bring this power to the front. So this is the same as x times log to the base b of b. We've just said, though, that log to the base b of b is 1. So this is equal to x times 1, or just x. The third kind of special case that you might want to be able to rewrite is when you've got a reciprocal. Because what we can do here is rewrite this as x to the power of minus 1. Because I can then use my power rule and bring it to the front. So log to the base b of 1 over x is actually the same as minus log to the base b of kind of regular x without the reciprocal, without it being written as a fraction. That's not as important, but it is useful to spot if you do notice it, that you can rewrite. So I could rewrite log to the base 4 of a third as negative log to the base 4 of 3. That's quite useful sometimes. The last one is log to the base b of 1. If we come back up here and look at this relationship, then what we're saying is that 1 needs to equal b to the power of something. When do we get an answer of 1? When we are raising something to a power. And that's when that power is equal to 0, which means that log to the base b of 1 is 0. So, and that's true for any value of b. So if you ever log 1, no matter what the base is, the answer is always 0. You can actually see that happening here. We could rewrite this one, instead of using the power rule, we could rewrite this as log to the base b of 1 minus log to the base b of x. Log to the base b of 1, we've just said is 0, so we've got 0 minus log to the base b of x, which is obviously negative log to the base b of x. So we can get there another way. We've got that same answer using a different method. So just to kind of go over that again, you've got your three laws here: the multiplication law, the division law, the power law. You've got some special cases which will crop up a lot in your work. Remember, you've got your calculator though, so if you forget that log to the base 7 of 7, if you forget what it is, you can just work it out on the calculator. The only problem you'd have, I guess, is if you had something like, if you had unknowns, if it was like log to the base p of p, you wouldn't be able to type that in your calculator. So they are useful to be able to learn. The very last thing I'm going to teach you today is that as well as being able to rewrite this in log form, which we already know how to do, so I'm going to just remind you that we know how to do that over on this side of the page. This would be the same as log to the base 5 of 60 is equal to x. You can also do something called logging both sides. So where you apply logs to both sides of the equation. And you're probably going to use this method more often than this method. This is why people forget this, is because everybody wants to try and log both sides all the time. If you can keep remembering this relationship, it's going to do you a lot of good. But instead, we can choose to log both sides. If you have a number that's a base, like this 5 here, then I would always recommend you choosing that number as your base, as kind of your first guess. It might not always be the right thing to do, but it's a good rule of thumb. So what I'm going to do is I'm going to apply the log to the base 5 to both sides of my equation. Okay, and I can do that because there's just a single term on each side. I can then use my rule, my power rule, to bring this x down to the front to multiply instead of having it as a power. And that's why logs are so useful. It's because it's going to take out unknown powers and bring them as multipliers instead. So it's unlocking that power. And hopefully in your heads, you know what log to the base 5 of 5 is. We just talked about that, but that's equal to 1. So we've then got x is equal to log to the base 5 of 60, which I know we had over here, but that will, it's more useful than it might appear at the moment. The other thing it means is if I hadn't chosen to use a base of 5, I could have used any base at all. If I choose to use a base of 6, then I've got, that's a 6, not a b. I've got a base 6 on both sides. I can still use my power rule to bring that power down. But what I can now do is divide by log to the base 6 of 5. Because these are just numbers, I can type these numbers into my calculator. So x will be equal to log to the base 6 of 60 divided by log to the base 6 of 5. And we can type that in on our calculator and we would get the same answer as we would have got if we typed in log to the base 5 of 60. I'm not going to do that now, but if you want to try that for yourselves when we finish talking, then you'll find that this answer up here, get my highlighter, this answer is exactly the same as this answer. And that's one of the really good, useful things about logs, is that you are in control of the base, and no matter what base you choose, you're still going to be able to get to the answer. But if you choose logs, if you choose bases sneakily, if you look ahead and think about what base will be useful, then you can sometimes save some time. Right, so that's all the kind of learning stuff. Again, I've got some examples to go through to just get you used to working with the logs. And this should then mean you can work through exercise 14E as well. So first thing to notice on this example is that the bases are the same. If the bases hadn't been the same, we wouldn't be able to do anything. The bases will always be the same, so you don't need to worry about that. We need to think about what rule I can use. And for this one, I can use my multiplication rule because I'm adding two logs together. So this as a single log will be equal to log to the base 3 of 6 times 7, which in this case we can obviously work out is log to the base 3 of 42. They're not actually asking us to work the answer out, they just wanted it as a single base, so as a single log. So that's the answer to question 1. Question 2, again, check that the bases are the same, which they are. This is going to be my division law. I've got a subtraction here, so I can say that that's the same as log to the base 2 of 15 divided by 3, which is log to the base 2 of 5. This is more like we're kind of heading a bit closer to what you might be expected to do on an exam. We've not looked at a question like this yet, so just have a quick look. Think, do you know what you might want to do with this? I'll give you a hint. I can't use the multiplication law yet. And the reason I can't is because it doesn't look like it. We didn't have a law with extra numbers at the front here. This law only works when there aren't extra numbers at the front. So what can I do to get rid of those extra numbers? What I can do is I can use my power rule backwards. I can bring these powers up here. So I can rewrite this as log to the base 5 of 3 squared plus log to the base 5 of 2 cubed. I can work that out. That's 9 and 8. And then I'm ready to use my multiplication law. I can bring these together and times them and get the answer of log to the base 5 of 72. So if you want to bring logs together but you've got multipliers in the way, then you need to bring them up as powers first before you collect together your 2 log terms or 3 log terms. You might have 3 sometimes. Okay, this is the other type of question that you might be expected to work through. And this time we're splitting them. We're splitting the logs. We've got a base of b. So what I'm going to do is I'm going to kind of look at my different terms. I've got an x squared term, I've got a y term, and I've got a z cubed term. They're all being multiplied together, which means I'm going to use my addition or multiplication law, which means I can separate these out into different logs with addition signs in between. And it says simplify. I'm assuming simplify means take the powers to the front. So I can bring this power and write that as 2 log to the base b of x. I don't need to do anything with my second term. And with the third term, I can bring that 3 down as a multiplier as well. So we're just kind of doing the opposite of what we were doing in those first 3 examples. I think this is my last, this is the very last example. This should help you get through the rest of the exercise. It says solve the equation log to the base 10 of 4 plus 2 log to the base 10 of x is equal to 2. So if we're solving the equation, we're going to need to work out what x. That's the key to this. Find what x is. So what can we do? Well, we've got 4 or 5 rules that we can apply. So it's all about thinking which rule will be useful. We're probably going to want to bring this as a single log. So in order to be able to do that, this 2 needs to be moved out of the way. So that's the first thing I'm going to do. I'm going to move that 2 so that it's written as a power. I'm then going to be able to bring these 2 things together as a single log using my multiplication law. And then I'm going to have to use my relationship between log to the base b of y equals x and b to the power of x equals y. So I'm having to come back to that first rule we used, because you can't unlog. You can log both sides, but you can't unlog. Well, you can, but you're just using this relationship. So that's what we're going to need to be able to do. So I've got 10 as my base, so that's my B. My answer is my X up here. So that's 10 squared needs to equal 4x squared. I can work out 10 squared is 100. I'm going to divide both sides by 4. And I can square root. Now, I'm going to, for this very only time, I'm going to write plus or minus 5. However, there is another rule that I've not spoken to you about yet, and this comes from the graph of logs. You cannot log a negative number with any base at all. If I do on my calculator log to the base 10 of -3, you get an error. You cannot log a negative number, which means if you get potential negative answers, you have to discount any negative answers. Okay, so in fact, even though when we square root we should write plus or minus, logs are very special in that if you get a negative answer that you could have logged, you need to eliminate that answer. So in this case, the only answer that works is that X is +5. Okay, so if you find yourself in a situation like this and you have written down that X is equal to -2, it's not true. That's just wrong. X cannot be a negative number ever. There's no exception to that. I think next week we're going to talk about the graphs of logarithmic functions, and you'll see why they can't have negative answers. But for now, just trust me that they can't. Okay, so that gets us to the end of the tutorial. You should now be able to do exercise 14D and 14E from the Year 1 textbook.